In this video we are going to introduce the basic concept of simple harmonic motion, and in future videos we will investigate the properties of simple harmonic motion in further detail. Right, we need to have a reminder about a really important convention about our diagrams. Suppose we've got a particle moving in a straight line and the x denotes the displacement of the particle from a fixed point on the line. Then it's important to realise that the positive direction for the velocity and the positive direction for the acceleration are the same as the positive direction for the displacement. So if the velocity is written as dx by dt or x dot, and the acceleration is written as d2x dt squared or x double dot, are indicated on their diagram, their directions must be the same as the positive direction of the displacement. Like this. Okay. We're going to consider a particle of mass 1.2 kilogram that's hanging at one end of a light elastic string of length 2.5 meters and modulus 19.6 newtons, and we're going to suppose that the other end of the string is supported or hung from a ceiling. Now in Unit 3 we discovered how to find the equilibrium level for the particle. So for equilibrium, we've simply got, using Newton's second law, vertically upwards, the tension in the string minus the weight of the particle must equal 0, because there's no acceleration in the equilibrium level. So T naught has got to equal mg. Now Hooke's law tells me that the tension in the string is going to be the modulus lambda, which in this case is 19.6, times by the extension, which in this case we have shown as being E, divided by the natural length of the string, which is 2.5, and that must equal mg, which is just 1.2 g. So, in other words, we've got E is 1.2 g times 2.5 divided by 19.6, which gives me a value of E of 1.5. So, in equilibrium, the string is going to be stretched by 1.5 meters. Now, at t equals 0, the particle is going to be pulled down by 1 meter and also given a downward velocity of 2.5 meters per second. And what we want to try and do is produce a mathematical model for the subsequent motion of the particle. So, in loose terms, the subsequent motion of the particle is it's going to start off moving downwards, and then at some point or the other one would expect it's going to stop and then bob back up again. That's not a particularly mathematical model, it's a heuristic model. It's what our common sense is telling us. Now you may well have met in Unit 3 the idea of a modelling cycle, where we start off with a real life problem, as we've got here. We make some assumptions and simplifications to turn that real life problem into a mathematical problem. We then solve the mathematical problem. We interpret the solution in terms of the real life problem, and then consider whether that solution actually is realistic compared to real life, or whether we need to go round and improve on the assumptions and simplifications that we made. So, the assumptions we're going to have to make in this case, well, certainly frequently in the past we've assumed that there's no air resistance. And the other thing we're going to have to assume is that the string remains taut at all times. In other words, that it doesn't get to a point where the particle is more than 1.5 meters above the equilibrium level. Now, if we're going to start considering the mathematical problem, what we really need to do is produce a force diagram for the particle at a general time t. And if we do that, we'll be able to start bringing Newton's second law in to try and find a differential equation for the motion. And that differential equation will give you, if you like, the mathematical problem that we've got to solve. So, there's my force diagram for the particle when it is at a distance x below the equilibrium level. So the velocity now can be written as dx by dt, and the positive direction for the velocity is the same as what we have just defined the positive direction for x as being, i.e. below the equilibrium direction, and that's also the positive direction for d2x dt squared. Forces we've got acting clearly just still mg downwards and the tension acting upwards. So applying Newton's second law downwards, we've got mg minus t must equal the mass times d2x dt squared. Okay, very useful shorthand which is used in maths is if we are differentiating with respect to t, instead of writing dx by dt, we can write x dot. Instead of writing d2x dt squared, we can write x double dot. So, what have we got? We've got the mass is 1.2 times by g is 9.8. Take away the tension. Okay, now using Hooke's law, the tension in this general position is lambda, that's 9.6, times by the extension of the string in this general position. Now in this general position, the extension of the string is the 1.5 meters down to the equilibrium level plus x. So we've got 19.6 times 1.5 plus x divided by the natural length, which is 2.5. So the resultant force is 1.2 times 9.8, take away 19.6 times 1.5 plus x divided by 2.5. That has to equal the mass times the acceleration, which is 1.2 times x double dot. If we now multiply out the brackets and simplify the left-hand side, we get 11.76, take away 11.76, take away 196 over 25 equals 1.2 x double dot. In other words, we've got x double dot is minus 98 divided by 15 times x. So we have the equation x double dot equals minus 98 over 15 times by x, or equivalently x double dot plus 98 over 15 x equals 0. So we've got the mathematical problem. It's x double dot plus 98 over 15x equals 0, together with the boundary conditions that when t equals 0, the value of x is 1 and the value of x dot, that's the initial velocity, is 2.5. So solving the mathematical problem is solving the differential equation that we've just mentioned, subject to the initial conditions that we've just mentioned. For the equation x double dot plus 98 over 15 times x equals 0, the auxiliary equation is simply k squared plus 98 over 15 equals 0. In other words, we've got k must be 0 plus or minus the square root of 98 over 15i. And that means that the general solution of the equation is going to be of the form x equals e to the naught t times by p cos the root of 98 over 15 times by t plus q sine the root of 98 over 15 times t. In other words, we've got x equals p cos omega t plus q sine omega t, where omega is the square root of 98 over 15. And p and q are constants that we haven't yet found. So we must now move on to the problem of finding the values of p and q. Now, if we've got x equals p cos omega t plus q sine omega t, then we certainly know that v, or dx by dt, is minus p omega sine omega t plus q omega cos omega t. If we consider the initial conditions, we know that when t equals 0, x is equal to 1. So that simply gives me 1 equals p times cos of 0 plus q times sine of 0. Cos of 0 is 1, sine of 0 is 0, so we've simply got p equals 1. We also know that the initial velocity is 2.5. So looking at the velocity equation, we can say that when t equals 0, v equals 2.5. So we've got 2.5 is minus p omega sine omega t, sine omega 0, plus q omega cos of 0. In other words, that's giving me q 2.5 equals q omega, so q must be 2.5 over omega. In other words, q is 2.5 times by the square root of 15 over 98. So we've now got our solution is x equals cos omega t plus 2.5 times by the square root of 15 over 98 sine omega t, where omega is the square root of 98 over 15. So if we return to our modelling cycle, we've now obtained the solution to the mathematical problem, and we need to think about interpreting the solution. And we know that this solution is x equals cos omega t plus 2.5 times by the root of 15 over 98, lots of sine omega t. So, with that solution, I've produced a little animation to show what happens to the particle during the subsequent time. So setting the animation off, and we can say that see that the particle is bobbing up and down, and the maximum displacement away from the equilibrium position is somewhere around about 1.3, 1.4. We can view a displacement time graph, so a graph of x against t for the motion. And again, we can see that the string doesn't go slack. It never gets to a point where it's 1.5 meters above the equilibrium position. So the animation and the displacement time graph verify that string doesn't go slack and that we have a simple oscillating system. Now, because the equation for x is entirely in terms of cos omega t and sine omega t, we can say that the period of the oscillation is going to be t. Period t is going to be given by t equals 2 pi divided by omega. We'll look at that later. Right, compare the solution with reality. Well, in practice, the amplitude of the oscillation will decrease with time due to the effect of air resistance, and an improved model would certainly take this into account. And later in this series of videos about harmonic motion, we will see how to deal with that. If you wanted to consider the effect of changing the initial conditions, the t=0 conditions of the motion, well, you could investigate that fairly easily if you have access to the GeoGebra app, which was used to produce the animation within this PowerPoint, and your teacher may well be able to provide you with a copy of that. This example that we've been considering is an example of what is known as simple harmonic motion. The formal definition of SHM is that a particle is executing linear simple harmonic motion if it is moving in a straight line in such a way that its acceleration is proportional to the distance of the particle from a fixed point on the line and is always directed towards O. Now, that verbal definition is rather a mouthful. There's a much neater mathematical definition of simple harmonic motion. What we're saying is the definition implies that the acceleration is proportional to x. So we've got x double dot is k times x. But the acceleration is directed towards O, so the value of k must be negative. Now, any negative number can be written as minus a positive number. And a positive number has always got a square root. So if we call the square root of that positive number omega, we can say that k must be of the form minus omega squared. So we can write the SHM equation as x double dot equals minus omega squared x, or equivalently x double dot plus omega squared x equals 0. So the formal definition of simple harmonic motion, if we want to express it mathematically, is it is a system that is moving in such a way that it satisfies the equation x double dot equals minus omega squared x. We'll be looking at the mathematical consequences of this definition of simple harmonic motion in the next video, and in subsequent videos we will be considering lots of further examples which prove to be simple harmonic motion.